Today we are going to take a look at what may feel like an unrelated topic to what we did last time. Last time, what did we talk about? Antiderivatives, and we did some formulas basically, right? Where we were going backwards from the way that we had done derivatives before. So this may feel like we're not quite connecting dots. I promise we will connect them. So just bear with me today, and there will be connections made over the next couple of class periods to the relationship between these ideas. But today we're going to talk about the concept of area. And we are going to use some notation that you may not be very familiar with. It's called sigma notation. This is the summation, that's what that notation means, of the first n terms. So you see this sort of Greek letter sigma going on there. The I equals 1 at the bottom tells you where the sigma notation begins, what term you're on. The value at the top tells you what term you end with, and it simply means to add up those values, starting with a sub 1 all the way to a sub n. I is called the index of summation. A sub I is the ith term. And then the upper bound is n, and then the lower bound is 1. So these are the upper and lower bounds on the summation. So I'd like to show you kind of what that looks like with a formula or an equation, right? So we're going to do this one. This is the summation from I equal 1 to 6. And the formula is 3i minus 1. So what we can actually do is to figure out each of the 1 to 6 terms. This tells me I start at 1. This tells me I end at 6. So I'm going to have A1, A2, A3, A4, A5, and A6. And those subscript numbers are the i's. So on the first one, A1, it means that I equals 1. So I have 3 times 1 minus 2, which would give me what? 1. And I'll do the next one, right? 3 times 2 minus 2, because I is now 2. What does it give me? 4. We'll do one more, and then we're going to take a pause for a second. 3 times 3 minus 2. 7. Do you see any relationship between the 1, 4, and the 7 that you could project what's going to happen next? Okay, you're adding 3 every time. Good job. So if you start to recognize a relationship, and some will and some won't based on the equations you're working with, feel free to fill them in. So then we've got 10, 13, and 16. Okay. So this actually, this formula, or this equation, when we do this and we create these terms, is actually called an arithmetic sequence. It simply means that I'm adding the same amount to get to the next term every time. So if I add the same amount every time, it's called arithmetic. If I were multiplying to get to the next term each time, it would be called geometric. You actually encounter those in high school curriculums at different points, so you probably have seen that idea before. And what we're doing with these now, though, is we're simply adding these all together. So I need 1 plus 4 plus 7 plus 10 plus 13 plus 16. And what do you get? 51 is it. Good job. The summation is 51. Okay, so my statement at the beginning about this feeling not like what we did before is correct, yeah? Yes, doesn't look like the same thing we've been doing. Okay, so there are some summation formulas that we're going to encounter next that tell us that if you have certain features or characteristics, there are shortcuts to finding the summation without having to find A1, A2, A3, all these A values, because if the A values go very long, right, like if I went from 1 to 50, I don't want to write out 50 terms. Even if I see the pattern is adding 3 every time, I don't want to write out 50 terms, right? So there are some summation properties that allow us to shortcut that system. Some of them are very simple to see why they should work. The first one is an example of that. If I add a constant to itself n times, what operation is that really known as? If I add 5 plus 5 plus 5 plus 5 plus 5 plus 5 15 times, how could you do that faster?
Square it?
Nope.
Or not square, but power it to power it.
It's not a power. We're going to get to one that is a power in a minute. This one's not. Multiply. Yeah, if I add 5 together 15 times, I could do just 5 times 15. You might remember even back to elementary school, people talking about how multiplication is just repeated addition. That's the idea. So if I added c to itself, c plus c plus c plus c plus c n times, that's really just c times n. N's the number of terms, right? That cap on the index of summation, the n at the top. C is a constant. It's a number that's being added. You may or may not have seen the second one before. The second one actually talks about what happens when you add numbers like 1 plus 2 plus 3 plus 4 plus 5. They're different every time, but they're just one greater than they were before. You add something to itself, not to itself, but to the next term multiple times. And there was a gentleman by the name of Gauss, famous mathematician, who actually sort of discovered this principle or this process when he was 6. So we can all feel like, oh, wow, today, right? Like at 6 years old, I was learning to add. Gauss was doing this. And what he figured out is that if you take n, and you add it to n plus 1, and then divide by 2, that is the summation of the first however many terms. So if you wanted to know, what do I get when I add 1 plus 2 plus 3 all the way up to 100? Well, you do 100 times 101 and divide by 2. It's a very nice shortcut because I don't want to add all those together, right? The story actually goes that that was exactly what his teacher did as he was probably first grade, I'm going to guess. The teacher gave them an assignment to add together the first 100 digits. Because that should take the kids a little bit of time, right? She probably need to get some grading done. And unfortunately for her, is that Gauss found the answer very quickly because he recognized some patterns and he came up with this kind of a formula. Crazy. Yeah, he's very smart. I mean, like if you go research Gauss, you will see like prominent mathematician, like I learned about him in grad school kind of thing, like very, very smart. All right, so if you do the same sort of thing, notice these are now powers, right? So I went from a constant to a power 1, right? That's I. And then I went to I squared, and then I'm going to go to I cubed. And there's very similar patternings continuing. So I'm going to have n times n plus 1 on this. But then I'm going to have 2n plus 1. And it divides by 6. So it was divided by 2. And now it's divided by 6. How would you get to 6 from 2? Like, what happened to the denominator? It multiplied by 3. Did you see that happen in our section last time, where all of a sudden the denominator multiplied by another value? When we were doing the antiderivatives, we divided by our new powers, right? Well, this power just got bigger, and now I divided it by 2 the first time when it was a power 1, and now I've divided it by 3 when it's a power 2, and it starts to feel a little bit like there's something connected. All right, one more. This is I cubed, and so this one is actually n squared and times n plus 1 squared over 4. So this would be adding together the first however many cubes. So the last one was squares. I didn't actually say that. It's written on your paper, but the sum of squares is number 3. So it would be like adding 1 plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, which is 16, right? Adding the squares together. This one right here would be adding cubes together. So 1 plus 2 squared would be 8. And 2 cubed would be 8. 3 cubed would be 27, 4 cubed would be 64, so you're adding the cubic values together to get that last one. So what we're going to do is we're going to actually use these properties to find summations instead of actually writing out terms to find summations. And we can do this very much like we did with integrals or antiderivatives like last time, or what we did with derivatives. If you've got things separated with addition and subtraction, you can separate them as well with summation notation. So if you take a look at this first one, I mean, I'm really only going from 1 to 16. You could verify this if you wanted to by writing out the first 16 terms. It wouldn't be horrible, right? It really wouldn't. And what you would do, though, if you're doing this with summation notation, is you'd separate. So we would separate this to I equals 1 to 16 of 5I minus the summation from I equals 1 to 16 of 4. So far, so good? Now, because I don't really want to write it again, and I know that most of you are using something that you can either erase or you can mark out if you're using a pen, the reality is that just like with antiderivatives and derivatives, constants come along for the ride. They do with summations too. That 5 does not affect the summation value except that it multiplies it by 5 when I'm done. So I'm actually going to put the constant multiplier in front. And the reason I am is because my goal is to show you that these pieces are exactly one of those 4 properties that I just presented. Okay? So the 5 in front will be multiplied when I'm done, but it doesn't actually change the process. It just, takes effect at the end. So it actually said the summation from I equal 1 to 16, or I equal 1 to n, would be taking, let me get it right over here, n times n plus 1. So for now, I'm just going to write those in as n and n plus 1, just to remind you, over 2. And then on the second one, this actually is property 1, right? It's a constant. So it should be 4 times n. But all of this is happening at n equal to what? 16. This is being evaluated at n equal to 16. So I can actually plug in the number 16 in each of those spots now. So I have 5 times 16 times 17 over 2 minus 4 times 16. And if you wish, either on paper or grab a calculator, somebody tell me what we get for this summation. We do, 616. Thank you so much. Okay. All right, so on this one, if we wanted to check ourselves, we could write out the n equal 1 term and the n equal to 2 term, or I equal whatever. We could write out all the 16 terms, and we could add them together, and we could verify that it really worked. But I'm telling you what, on this one, that is probably not in your best interest. There's something interesting that's happening on this, and a couple of things that make it different, though, besides the fact that it's a large number as our n value on top. Can somebody identify a couple of things, one thing, just maybe one thing that you see that makes this different? It doesn't start at I equal 1 or n equal to 1. The number at the bottom is not 1. Do you see that? We're going to have to be careful about that. There is something different we have to do. It matters. What else do you notice? We need to simplify the inside. What were you saying, Rod Anthony?
No, just n squared minus 1.
Yeah, we need to do n squared minus n, right? We've got to simplify what's inside in order to apply the properties that we have used from the previous slides, right? So that is the first thing that I need to do. We will deal with this n equal to 4, I promise. But let's start with the simplifying of what's actually written here. So this is the summation from n equal to 4, n equal 4 to 140. If you don't like n as the subscript down there, change it back to i's. I don't care. Just they should match, but it really doesn't matter. Some books will use j's and k's even. It's irrelevant. But I have, like you said, n squared minus n, right? And I'm going to separate this out. So the problem is that all of my rules all start at the subscript on the bottom, right? That index at the bottom equaling 1, right? Are you with me? And this is supposed to start at 4. So I can't just go applying those rules without compensating for the fact that those rules they only work if I start at n equal to 1 or I equal to 1 at the bottom. So what am I going to do? Well, what we're actually going to do is we're going to change it so that it is n equal to 1 at the bottom. But of course what that means is I added on an a sub 1 term, an a sub 2 term, and an a sub 3 term that really aren't there. Are you with me? So if I add something in that's not there, what am I going to have to do to compensate? Subtract it off. So at the end of all this, and this part I can get from my properties, I need to make sure I subtract off A1, A2, and A3. Because they're really not supposed to be in my summation that I'm asked for. So I will have to compensate for that. Now, that said, I can actually take these quantities now. So this is the summation from n equal to 1, from n equal 1 to infinity of n squared, minus the summation, and I don't know why I've got infinities there. I do know why, but it's not supposed to be. It's supposed to be 140. Sorry about that. Okay, 140. N equal 1 to 140 of n. And then I'm going to subtract off, and I'll figure out the A1, A2, A3 in a moment to do that. All right, but n squared, or I squared, if you go back and you look, what is the actual formula or equation that it's telling me to use when I have I squared?
N times n plus 1 times 2n plus 1 divided by 6.
Yes.
Sorry.
Good job. And then how about for n? Or I, if it were just the variable, or not the variable, but the...
Plus 1.
n times n plus 1 divided by 2. And I'm going to evaluate this at n equal to 140, right? And again, I still have at the end here. I'm going to leave them hanging until I'm calculated the other stuff. A1, A2, A3. If you want to calculate them now, it's fine, but I'll just hang on to that for a minute. Okay, run out of space. Okay, n equal to 140. So I have 140 times 141. I need 140 times 2, that's 280 plus 1, so that'd be 281 all over 6. Minus, now I have 140 times 141 divided by 2. And again, I need to subtract A1, A2, and A3. Okay, so let's calculate each of those first two pieces that are not my A1, A2, A3s and get a value for that. I don't even know that I have a value separated for this, but somebody can tell me. $924,490. Does anyone else confirm? I think my answer in my paper is not that large. It's close though.
914620.
Okay, that's what I think I have too. Double check your, you probably just have a number in the wrong spot on there. I have 914. What'd you say, Emma?
914620.
Okay, I think that's what I'm supposed to have too. And then I need to know what A1, A2, A3 are. So let's actually find those now. So A1 means taking this and plugging in 1 where n is. So that would be 1 times 0, which is 0, yeah. A2 would be 2 times 1, which would be 2. And then A3 would be 3 times 2, which would be 6. So at the end of this, I need to subtract 0, 2, and 6. Does everybody understand where A1, A2, and A3 came from with my equation?
Could you do it again, please? Or
Yeah.
do it again?
What I'm trying to do, oh my goodness, different class, hang on. I need to change the thickness of that. So I'm using this equation, and I'm evaluating it at 1, at 2 and at 3. So if I plug in 1, I get 1 times 1 minus 1, which is 0. If I plug in 2, I get 2 times 2 minus 1, which is 1. And 3 times 3 minus 1, which is 2. Okay.
I thought you wanted just the value of the first thing. That's what I did it for, not subtracting.
Oh, I see. Gotcha. All right. 914,620 minus 0 minus 2 minus 6 gives me what? 914,612. Okay, so fun stuff with summations, but that is not the title of the section that we're working in. The title said area. So what is the connection? Well, the connection is exactly what happens next. So now that we understand how these summation notations work, we're going to apply them to areas under curves. So if we took just a general shape of a curve, and I've done a cubic one here, and we wanted to approximate the area from my first hash mark, which is about right here, to my second hash mark about right here, and we wanted to shade in all of this area under the curve down to the x-axis. Like if I asked you when you came in today, do you know how to find area? I imagine most of you would have said, sure I do. But your definition of what I meant by area would have included things like rectangles and squares and circles and triangles, right? And this shape is none of those. So our goal is to be able to find this red area with this curved top. I've got straight edge sides, right? And I've got a straight edged bottom, but I've got this curve on the top that causes me to not be able to use a lot of my standard equations that I'm familiar with for area. But we can actually approximate the area of this shaded in red region by using something we do know. You know how to find the area of a rectangle. What's the area of a rectangle? I promise I'm not trying to trick you. Length times width. You know how to find the area of a rectangle. It is length times width. Now, obviously, I can take the length of this segment, right? I mean, the length right here, no problem. You could do that. The problem is that the width or the height is not the same throughout the region, right? Some of those heights are much larger than other ones, and it's changing constantly. I don't have a constant height to be able to multiply by this width or length. So what do? Well, what we're going to do is we're going to take portions of this and subdivide. So I'm going to take my region. I'm just going to draw the picture with 4 because it's easier to draw that way. I'm just going to divide my width of my rectangle into 4 smaller pieces. 4 is nice because you can half it and half it again. And we're going to create these lines. They're supposed to go straight up to my curve. Let's try this instead. And if you can imagine, at least when I've made it a little bit smaller, the height doesn't vary quite as much as it did over the whole region, right? I mean, it's still a curve on top. It's still not a straight line segment, but it's not near as drastic of a fluctuation as it was before. And if you could picture in your mind without drawing it, because it's going to mess up your picture too much more, if you subdivided them again and made 8 little rectangles, it would get even better, right? Every time I make more rectangles, the height's going to vary less than it did before. So what we're really going to be doing is taking this idea of rectangles, which we know how to find the area of, and finding more and more and more little bitty rectangles that we can calculate areas for instead of the larger rectangles that have too much variation in their height. So we're going to talk about 3 ways of doing that, all with rectangles. One way of doing that is using what are called left endpoints. The second way is going to be using right endpoints. And then the third way is to be using the midpoint of these rectangles. And again, I'm going to draw the picture with 4 rectangles because it's so much easier to see. The more rectangles, the more messy your picture gets. But the process works whether you have 4 rectangles or 6 rectangles or 7 rectangles, heaven forbid. I don't want you to divide anything into 7 pieces. That's not fun at all. But no matter how many rectangles you have, this process will work. I'm just going to draw the picture with 4. So we're going to do the same thing we did just a moment ago. I'm going to draw these areas up and create those rectangles, trying to subdivide my region into 4 pieces that are approximately equal width. They should be actually equal width, but my picture is going to be approximate. So this method is going to use left endpoints as the height. So if you take each of these rectangles, so let me imagine this, I'm going to draw it in a circle right now, actually a square rectangle shape itself. If you imagine this shape right here, okay, the first rectangle that I need a height for. This method says that the height is going to be found by using the endpoint that's on the left. So the endpoint on the left would be this one, right? It's on the left-hand side of the 2 sides of my rectangle. And what I'm going to use is I'm going to use that as the height of the rectangle, go straight over and straight down. And then I'm going to do the same thing for my next rectangle. The left point would be this point, and I'm going to go straight over and straight down. So clearly, when I find those areas, I am overestimating. Agreed? Those are overestimates because I've got space that I'm counting above that's really not under my curve. But as luck would have it on this particular curve, as I keep going and I use my left endpoint, this next one is an underestimate. I'm not getting quite all the area that I should have gotten. And if I do it again on this point, on the left, the rightmost rectangle's left endpoint, I get this one. So on this one, this process appears that it might sort of balance itself out. I'm overestimating in some rectangles, I'm underestimating in other ones. It's probably going to be a pretty good estimate overall, but that's simply because the curve I chose. Had the curve been different, this might just flat out be a really bad estimate. It might overestimate every single time or underestimate every single time. But the area I'm going to get, can I see that? Not very well. Let me try a different color. The area I'm going to get is going to be the area of these rectangles. It's not actually going to be an exact value of the area under the curve, but it's going to be these. Okay, so I want to put a little bit of notation to what we've done now. Okay, so this is the visual of it, but let's do a little bit of notation for what's happening here. We're actually going to call that first interval endpoint x0. The next one is x1, x2, x3, and x4. So far, so good? Okay. Now, all of these widths are the same if I've actually split my interval up evenly, which I attempted to do visually, right? They should all have the same width of the rectangle, agreed? And you know that an area of a rectangle is length times width, okay? So we've talked about that. Area is length times width. But the width of each of my rectangles, at least it should be, all the same, this distance across, is the change in the x value. So we're going to use delta x to represent that. Delta simply means change in. Just like when you found slope back in the day, right? Delta y over delta x, right? Change in y over change in x. So what we're going to do if I find the area of this first rectangle is that it's length times width. Well, the width is delta x. The length, or height in this case, is what? How is it found? At what, Emma? I feel like you're about to say it.
Is it x1 plus x0 divided by 2?
That's what it's going to be. We're going to get to that later. It isn't on this one. So think more visually. Where is the height actually being determined by?
x0.
X0. Whatever the height is at x0, that's actually what's determining what's going on. And if this equation, we'll give it a name so that I have some notation to do it, is f of x, then if I found the x0 value and I plugged it into the equation, I would get that point on the curve, right? Plug in x, you get out a y, and y is the actual height of my curve. So it's x delta x times f of x0, length times width, right? One of them is the height of the rectangle, that's f of x0. The other one is the width of the rectangle, which is delta x. How about the next one? I'm going to run out of space, so I'm just going to keep drawing my picture a little bit differently. This is another delta x, but what's the height on this one?
x1
It's at x1, so it's f of x1, right? What about my height on this one? Well, its width is delta x. What's my height? F of x2. And then my last one, again, a delta x, and it's f of x3. Because I've used the first 4 of the 5. I have 5 endpoint values I've labeled, x0 up to x4. And I've used the first 4 of them as my first 4 heights because it is the left endpoints I'm supposed to be using. So far, so good? Okay, but the goal then is to take all those areas and do what with them? Add them together. So what I actually want to see is I want to see delta x times f of x0 plus delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3. That's what I want to see. But what do all of those have in common? Delta x. So I'm telling you what, I don't want to multiply something 4 times when I could multiply it once and get the same effect. So if we think about that sort of in reverse, I can factor out the delta x, and I'm really just going to be adding up f of x0 plus f of x1 plus f of x2 plus f of x3. But what you see here is a summation, like we just did on the previous slides, right? Sigmas and all. So how else could I write this? I'm totally running out of space here. Let me do this. You know what? Yeah, I don't have space on the next slide. Okay. I'll just shift that up there for a minute. So what does this look like instead? Well, the delta x is just a constant. It's just a number, so it can be pulled in front of my sigma notation. And then I've got a summation, and this particular summation starts at 0, and it goes to 3, because those are my subscripts on my x values, right? x0, x1, x2, x3. And I'm adding up f of x sub I. And again, all this is saying is add 4 y values together and then multiply them by the distance that your x values are apart. So if we go through this process again, which we are, but we use the right-hand endpoints, we should be able to jump to the conclusion statement I just made more quickly because the same thing's going to happen. So draw the picture again, as in draw my rectangles in here, or at least my 4 width pieces. They're not perfect, but they're okay. I've got my same x0 to x4. But on this slide, I'm supposed to be using the right-hand endpoints. So if I imagine that first rectangle, this piece right here, instead of x0 being my height, what's going to be my height? The value at x1 instead. So this point right here measures my height. For the first rectangle, which means it looks like that. It's the height. For my second rectangle, what am I going to use? x2. My third rectangle, x3. And my fourth rectangle is x4. Now again, because of the shape I've done, this doesn't seem like it's going to be all that much different. I've got some overestimates, I've got some underestimates, and that's all well and good, but that's because of the curve I'm using. Different curve, different results. The first one I did might be a complete, like, huge overestimate, and this might be a complete, huge underestimate. Like, that's legit. We can actually have that happen. And if I were adding these areas together, I'm going to have the same kind of thing happen as before. I'm going to end up adding a bunch of heights together. But the heights are going to start at what value? X what? X1, and they're going to go to X4. Instead of X0 to X3, the first 4, they're going to be the last 4. Oh, I lost my screen. All right, just a second. All right, we're back on, and we're here. Okay, so we had said we had that same delta X value as our width on all of ours, and that we are doing a summation of 4 heights, but the heights actually start at 1 and end at 4 instead of starting at 0 and ending at 3 of the f of x sub I values. That's what those look like. Okay, everybody good with that? All right, my third one is not as clean to write down in a concise form like this, so I'm not going to write it down quite like that, but I do want to show you how you go about doing it because it's not any different of a process. There's just one piece at the end that is a little different. So again, we're going to make those heights on my rectangles. And what we're going to be doing instead of finding the left end point or the right end point is we're going to use the midpoint. So if I have x0 and x1, I'll just label those for now, and I want the point halfway in between, obviously, kind of like Emma had just said before, you could add x0 and x1 together and divide by 2. If you had real values, that would not be a difficult thing to do. It's just averaging. I don't want to write it down with these values because it looks really like it's complicated. But here's where you would be approximately, and that would be your height then of your rectangle. And so you would go to the right with that. Hang on, let me use red. And you would go to the left with that. So in this particular rectangle, it would overestimate a little bit, it would underestimate a little bit as well. But again, depends on the rectangle you're working with. And we would do the same process all the way through. So I'd find the midpoint between the 2 left and the right hand endpoints, and I would use the y value at that midpoint to create my height. And I'll shade them in. So we use points in between as my 4 heights. Notice the widths are the same. I do recognize that you could sort of look at this and feel like you create 8 rectangles, and I get that. But really, there's still just 4 rectangles here. Okay? So I still have a width that's exactly the delta x I had before. That's not any different. I still just have 4 rectangles. So we absolutely have to do an example with numbers in it so that you can see how this all plays out. So here's our example. We're going to do a left end point, a right end point, and a midpoint. And we're going to do it for n equal to 4. As you're doing your homework, you're not always going to have n equal to 4. You might actually have n equal to 6 or n equal to 8 or something like that, okay? But we're going to do n equal to 4 on this one. We have an equation, f of x equals 2x squared plus 5. So what I'd like to start with is by asking you either to graph it if you don't remember with your calculator, or if you remember to think about and to sketch approximately, it didn't have to be perfect, but approximately what the curve would look like. It's on the interval from 0 to 2, right? And we're sketching the graph of a parabola. So we're going to start at 0, and we're going to end at 2. And it's a parabola, and I mean, I guess I've already sketched my axis in there to lead you down the right path, but is it above or below the x-axis? Above. The plus 5 at the end tells you that the y-intercept is actually 5 as well, right? So my y-intercept is here, and it's a parabola from there, so it looks something like that. Is that okay? The curve is really not for the purpose of being able to make conclusions from, but it is for the purpose of being able to help you figure out the endpoints you need and things like that. I know some of us are more visual than others, so it might be more necessary or less necessary for you in particular, but I'd like to see you draw the curve, okay? So I'm supposed to have how many rectangles? 4. So I need to actually take, that is one end. Hang on, let me use a different color so I can see it. That is one end, and this is one end. And I need to split the interval into fourths. So if I split it in half, what's the x value at the bottom going to be that I'm using? Yep, it's 1. And I need to split them in halves again in order to get fourths. So if I split them in halves again, what are my x values where I am? And you are welcome to use decimals or fractions. I don't care at all. So either 1/2 and 3/2 or 0.5 and 1.5, whatever you like. These are the 4 values. And we're supposed to find the left, the right, and the midpoint. So I'm going to split them as though they're like 3 parts to the problem ABC. And I'm going to call the left-hand endpoints L of x. I'm going to do the right-hand endpoints R of x, and the midpoints M of x, just to remind ourselves which one we're on. Okay, so I'm supposed to take every single time the width of the rectangle and multiply with it. So what's the width of each of these rectangles? 0.5, you bet. And then I'm going to multiply it by the 4 heights that you would use if you're doing the left-hand endpoints. So they're all going to say f of something, right? What is the first left-hand endpoint? F of 0, yes. What's the second one? F of what? A half, So either 0.5 or 1/2 is a fraction. What's my third one?
1.5. Wait, 1.
1. And then the last one would be 1.5. And I'm definitely writing too large. Let me make this smaller. All right. So in your calculator, you can do some really cool things. So if you have your calculator with you, grab it for me today. This is cool. I wish I could display so you could see mine doing this for you, but I think we can walk through it without it and we'll be okay. In your y equals, I'd like to put the equation that you're working with. So in this case, it's 2x squared plus 5. Everything that I just wrote, I expect to see right. Okay? But I do not need to see the exact value for f of 0, the exact value for f of 0.5, the exact value for 1. I don't need that part. Okay? I want to know that you've found, you know how to calculate it, but you can use your calculator to do that. So here's how you do it. You already wrote it in y equals, right? In y1. Go back to a regular screen, not a graphing screen, just the plain computation screen. And I want you to hit vars. Y vars. Function. And then at y1, you can hit enter, and you can put a parenthesis and tell it 0. So it should now say y1 of 0. What's that? Oh, I don't want you to press enter. That's okay. Keep it going. Sorry, I didn't think about that. That's fine if you did, but you don't need to. Here's what I want to show you can do. You can tell it then do plus. And you can do vars, y vars, function y1 of 0.5. Plus vars, y vars, function y1 of 1. Plus vars, y vars, function y1 of 1.5. And then press enter. So I'm just going to come around and make sure you kind of see what I'm seeing. Okay. Yep, that's where we are. Yep, like that. Yep, okay, very well. Just keep going. That list. Looks good. You're trying to enter. And I don't know, you might have to search online for that. You're looking at his. Okay, are you doing okay there? Okay, hey Eric, is yours looking okay? Okay. Operating with the right idea, I think. And I don't know. Yeah, you got 27 again. Okay. Oh, you can leave the times 45.
Yeah.
Okay, and then after you've gotten the 27, this is 27, if you hit times 0.5 or divide by 2, it will tell you the final result, which is 13.5. So this area is approximately, using this approach, 13.5. Now here's what I want to show you. We're going to write down the next one, so just write with me for a minute. Don't touch your technology, because I want to show you how cool your technology can be without you having to enter it all again by hand. So we're going to do R of X, left, right, and it's 0.5. What are the 4 X values I'm going to use for the right endpoints, though?
Just reversing over 0.5.
Yeah, I'm going to start at 0.5. So I'm going to 0.5, 1, 1.5, and 2. So I'm going to write those in. F of 0.5 plus F of 1 plus F of 1.5 plus F of 2. Now, I'd like for you, before we go doing too much work here, to compare these. How are they different?
Starts at 0.5, 2. First one's 0.
Okay, so there's some of it that's the same, right? Parts of this are identical, agreed? What parts are identical? The first 3 on this on R of X and the last 3 on L of X. Those match, right? So in your calculator, if you simply go, I want you to try this. I want you to hit second, enter, second, enter. You got to do it twice, and it'll bring up the line where you did all the additions. Okay? Bring up the line you did all the additions. And if you will simply change y1 of 0 at the beginning to y1 of 2, which is your last value, it keeps all the other 3 the same because they're the same, right? I need all of them just like I had them before, and I press enter and it recalculates, and I didn't have to enter it all again.
The first part.
Second enter, second enter. You hit it twice.
Enter.
I just clicked yeah, like I just clicked on it and brought it down.
Oh
Here's
my
different.
gosh.
Isn't that cool? How did that happen? It won't work like that. Mine doesn't anyway. Yours might have a different operating system. Mine won't do what you described. His is an Inspire, which it does all sorts of different things. So maybe a second, and then one more time. Oh, you've got to hang on, just do this. And then go over here and change it 0 to a 2. Okay. Did anybody not have success changing their 0 to a 2 or getting it to pull back up? Do you have it? Okay. Oh, Inspire. Talk to Maurice. Hey, Maurice. Can you help Jackson out?
Nope, he has the
Oh,
same that I
Oh,
have.
never mind. We have the same.
Yeah.
I can't help you out. I'm so sorry. We can probably play with it after class if you like. Did you get yours to work out? Okay, cool. It should say 35. Did everybody get a 35? Who tried? Just go to the very beginning.
Oh, yeah, you
and change the
just
first
say
one.
it.
Just slide 0 you don't
Yeah,
want. You
you
want
just
to
say
see what you
The old ones, one, the year behind our stuff.
There's 35.
And the cool thing about this one.
Yours shows up in the graph.
How you doing over there, Mateo?
It's
working okay? Are you good? Roland? Yeah?
Yeah, there's
It's
another one.
35?
One's better.
Yeah, it's the part that's.
The 0.5 at the beginning.
The first part?
Oh, you got usually it's 35 halves, so it would be, yeah, it'd be right. It should be 35. Okay, after you get 35, you can press divide by 2 again, or times 1/2, and you get 17.5. So yeah, it is 17.5. Now, that's great for the left endpoints, right endpoints, but it doesn't work so pretty for the midpoints. So let's go through the process for the midpoints. M of X. It's still 0.5, right? And I still need 4 X values, but the X values I need are not currently marked on my graph. So let's talk about what they should be. Uh-huh. Say that louder for me. Yeah, the first one's 0.25. So I'm going to have F of 0.25. And the next one, halfway between 0.5 and 1, would be 0.75. And then halfway between 1 and 1.5 would be 1.25. And what would my last one be? 1.75. This one's fairly nice because you can think of it like you think of money, right? Quarters and $half and things like that, halves of dollars. All right. I don't have any cool calculator tricks. It's just kind of messy because you have to re-enter it. You could go back and do the second enter thing if you wish, but you're going to have to change all of them. So I don't know that it's really going to save you any time to do that necessarily. But go ahead, calculate that. I will too, just to make sure. And then multiply it by 1/2 or times 2. And what'd you get when you get it?
15.25.
That's what I have as well. After you've divided by 2 or multiplied by 0.5, 15.25 is what you should be getting for the final result. So I'm fully aware that your web assigned homework means that you don't have to show any work, but when you get to the point of the test, this is what I would expect to see. So whatever that means between now and then of practicing so that you remember that at that point, make sure you're doing that because I will want to see those pieces. If you want to show me more, you can. If you feel like that's going to make sure that you're more accurate or more careful in the process, but this is the bare minimum. Okay? Any questions? Okay, so one real quick thing before we finish. This is 4 rectangles, and in part because it's easy to draw, right? But if I had 8 rectangles, I would be getting a better estimate, right? And if instead of 8 rectangles, I had 16 rectangles, estimate's just going to get better. Every single time, more rectangles, better estimate. So what we're going to see happen next time is that very thing. What happens when I get infinitely many rectangles? How does that work? And I'm going to tell you right now, it doesn't calculate like this. We're not going to go through these derivations. But that's where these derivations actually lead to, is the process of doing this infinitely many times. All right, so this lesson, section 4.2, is due on Tuesday. Have a lovely, lovely Easter.